What exactly does figuring out if aliens exist have to do with the end of the world? Well, it turns out that the odd emptiness that we find in the universe can give us clues about what may have gone on or didn't go on before we humans came along. Did something bad happen? And if so, might it happen to us too? Looking around for signs of whether we're the only intelligent life to have ever evolved can help answer those questions. And when you look at it, the universe does seem amazingly large for Earth to be the only planet with life on it. Consider it like this. Let's say that you're a photon, a tiny packet of light, and one day you had the wherewithal to set out to travel across the universe. You would find that, perhaps to your great surprise, such a trip would take you around 50 billion years. Yes, you, light, which can travel at the speed of light, would take 50 billion years to cross from one side of the universe to the other. At least, that's how long it would appear to take you to us humans. And this is just the observable universe, the amount of the universe that light like you has had time to travel across since the Big Bang. Within that vast space, there are anywhere from 100 billion to 2 trillion galaxies, by our current guesses at least, of which our own Milky Way is on the larger side of the spectrum. There are larger, but there are also a lot of smaller ones too. Within these billions or trillions of galaxies are billions and billions and billions of stars, and probably exponentially more planets. The total number of planets and stars in our universe, the total number of places for life to exist, is mind-bogglingly large. And so you, packet of light, or wavelength depending on your mood, might think to yourself as you traveled across the universe and saw that the Earth is the only planet that is home to intelligent life out of the 10 to the who knows what power planets that could host life. You might think to yourself in your little photon voice, what a waste. Are we alone in the universe? And if we are alone, why? These are the questions at the heart of the Fermi paradox, and they continue to nag at us. The answer is plainly obvious if you look at it, but it depends on how you look at it. With the Fermi paradox, the same thing can look very different to any two people. And it's not just the paradox itself. Even the evidence is equally ambiguous. It's all like one big contronym, words that have two meanings that are the opposite of one another. Like how weather can mean both to wear away and to withstand something, the size of our empty universe can mean that we are both alone or one of many. Another example of this ambiguity is the very presence of life on Earth. Something that people who believe that we're not alone in the universe point to as evidence is that life here on Earth seems to have emerged the first chance that it had. The famous astronomer and science writer Carl Sagan was one of those people. He was an optimist when it came to the Fermi paradox. He believed that life was out there, we just hadn't found it yet. Sagan pointed to evidence from the fossil record that here on Earth, life began as early as 500 million years after the Earth formed. It was almost like it was waiting to emerge. And since it emerged quickly here on Earth, it stands to reason that life should emerge wherever it gets the chance anywhere in our universe. When you take into account the idea that there are perhaps 300 billion stars in the Milky Way alone, even if some small fraction of those have habitable planets that could host life, then we should expect to encounter it sometime soon as we spread out to explore the countryside around planet Earth. But there's a problem with basing our view of the rest of the universe on our own existence. The idea that we can gain insight into our universe from our existence is called the anthropic principle, and it's vulnerable to a logical fallacy called selection bias. Being the only intelligent life in the universe, we're the only data point in our data set, and so we tend to skew the results a little bit. It's hard to resist the temptation of cherry-picking the data when there's only one cherry. Yes, of course, life can arise. Our very existence proves that fact. But what it does not prove is that the emergence of intelligent life, or any life really, is easy or inevitable. What if instead, life emerging in our universe is really, really, really hard? Perhaps the existence of living, breathing, intelligent things here on Earth doesn't show the emergence of life as inevitable, Perhaps it shows that it was the singularly most unlikely event in the history of our entire universe. If you could crack open a strand of your DNA and read the pairs of adenine, guanine, cytosine, and thymine, the ones and zeros of your genetic code, you would find a history of life on Earth written into it. Not only does your DNA contain the blueprints for making a full version of you, but if you look at it correctly, it also bears the marks of those who've come before you. You'll find your parents' genes, of course, and their parents. But as you go further back in time, you'll also find the contributions of all of the animals and bacteria that ever reproduced along the last several billion years to form a connected chain of life that eventually led to you. But you'll find that you run into a wall the further you go back. There is a point beyond which we can no longer read the tea leaves of our DNA. It ends right before we get to the emergence of life here on Earth, the very beginning. That is to say, no one is sure how life began. As it stands now, the general consensus among science is the concept of abiogenesis, that life emerged from nothing living anyway. Let's go back to the early Earth, about 500 million years after it formed. The surface has just begun to cool enough that solid clay ground has begun to form, and with the cooling off, the muggy atmosphere cooled as well, condensing into rain that began to collect in pools, which would become the petri dishes where life took its first steps. But to get from here to life, something extremely unlikely had to happen. Plain old lifeless molecules had to spontaneously arrange themselves into new forms that became the building blocks of life. At this point, there was nothing but raw materials on Earth, and we have to get from here to living organisms. That means that not only do you have a functioning organism, it has to carry with it the encoded instructions to make a copy of itself, and some way to read those instructions and actually make that copy. It's like the idea of putting some plastic pellets and metal shavings into a bucket and expecting an autonomous 3D printer to form from it. Or, more to the point, it would be like the idea of rotting meat growing maggots. For a long time, humans thought that this kind of thing, spontaneous generation, was how some life arose. Prior to when science took up the mantle of explaining our universe, people relied on their everyday observations to explain occurrences like maggots growing on rotting meat, seeming to appear out of nowhere. It seemed just as likely as anything that maggots could spontaneously generate, or baby mice from grain, which was another common folk belief. But eventually scientists figured out a way to disprove this idea, which really gained support when we realized that tiny, unseen life lived around us everywhere, and that it had a hand in a lot of the things that we saw. Germ theory was developed, and the concept of spontaneous generation was abandoned. That is, until the 1950s, when researchers started working hard on figuring out how life on Earth might have come about. Spontaneous generation made an unexpected comeback. Abiogenesis holds that quadrillions upon quintillions of simple molecules present in Earth's early atmosphere and oceans randomly configured themselves into a mind-bending number of different combinations. Some of these abominably large number of combinations happen to create useful complex molecules like amino acids, which are the precursors for proteins. Now, it's one thing to form simple molecules to randomly combine to form more complex molecules, but there is still the issue of replication. If those molecules don't make a younger copy of themselves, that innovative chemical chain is broken, and the new molecule loses the chance to continue to evolve into new and even more complex things. And this is the point where science is currently stuck. Somehow, they say, some of those molecules manage to form a stable string of nucleotides, probably RNA, ribonucleic acid, which is capable of doing two very important things. It can encode information in its nucleotide chain, and it can also transcribe those nucleotides to produce proteins. And once you have proteins, you can do all sorts of things that supports life. Back in 1953, two organic chemists, Stanley Miller and Harold Urey, sought to show that this was possible by recreating the conditions of early Earth in a flask. They simulated a primitive ocean and built an atmosphere out of the gases thought back in the 50s to have been present on Earth soon after it formed. They mimicked lightning storms with a flickering electrical current. And when Miller inspected the broth that resulted, he found that 19 amino acids and amines, the precursors to proteins, had assembled spontaneously.
Come look at this.
It seems that Miller had shown that when the conditions were right, the foundations for life would arise. But lately, the idea that abiogenesis just happened randomly is falling out of favor. Instead, some scientists have begun to suspect that there is some set of organizing principles that serves as a driving force for life to emerge. Just like how gravity will draw a ball downhill, or how magnets will always repel or attract one another when they're close together, there is some fundamental governing force of nature that causes life to assemble along predictable lines. We just haven't figured out what that force or those lines are yet. This is a pretty surprising idea if you think of it. One of the laws of the universe, the second law of thermodynamics, is that things tend toward disorder, not order. The idea that when presented with the right conditions, dead molecules in the universe will organize themselves into something living and breathing runs totally counter to that. And this new view also includes evolutionary biology as one stretch of these organizing principles of life. So the idea is that molecules arrange themselves into self-replicating, metabolizing parts that form increasingly complex beings that eventually include you and me.
Hello.
Which makes you wonder what the end point is. To some people, the idea that life arose from simple dead molecules that just happen to randomly assemble themselves into living things is just too unlikely to accept. And even if we do accept that this is precisely how life arose on Earth, the idea that it could ever happen again anywhere else is too improbable. It virtually proves that we humans are alone in the universe. One issue people raise is time. They say that Earth just simply hasn't been around long enough for all of that random chemical trial and error to have taken place. The idea that life organizes along some unknown universal principles definitely addresses that idea of time, and so does panspermia. Panspermia is a concept from astrobiology, and it says that the seeds of life are all over the universe in abundance everywhere. They can be found on board asteroids and other celestial objects, and that these seeds of life are constantly bombarding planets all over the universe. If the conditions on the planet happen to be right, well then those seeds of life will germinate and grow into something new and living. This certainly addresses the issue of time. Life could have evolved elsewhere in the universe, which is billions of years older than Earth, and then spread to our planet aboard an asteroid. We've recently found that some chemical precursors to life can be found on celestial objects like asteroids, and that they're able to survive re-entry into an atmosphere, which can get pretty hot. This is important because it's widely accepted that an atmosphere is a precondition for life to emerge. If you take panspermia and you take the recent view that life follows some organizing principles as immutable as the laws of physics, then you arrive at a conclusion that Earth is just another place that happened to have the right conditions when a rock bearing the precursors to life landed around 4 billion years ago. In this view, then, of course life is abundant in the universe. But then we find ourselves right back to where we started. Where is everybody? Perhaps the best answer to that comes not from an astrobiologist or an astronomer, but from an economist named Robin Hanson, who proposed that there must be something, some incredibly difficult step between the point where dead matter forms life and the point where intelligent life becomes a galactically colonizing civilization that no species has ever been able to overcome. He calls it the Great Filter.
Every piece of matter in the universe is the sort of thing that could have started that process, started life and then advanced life, etc. But so far, nothing out there has done that. So the Great Filter is whatever is in the way. Whatever makes it hard for any one piece of ordinary dead matter to produce expanding, lasting life.
There's surely a countless number of steps along the path from dead matter to the emergence of a galactically visible civilization. But the Great Filter hypothesis supposes that a handful of them are really, really hard. and that one of them in particular must be so hard that it has thus far prevented any life from reaching galactic proportions. This is Oxford University philosopher Toby Ord.
If there were 100 pieces, you needed to get into the right order in order to create something that obeyed natural selection and was at the basic level needed to actually bootstrap up towards complex life. Then there are 100 factorial ways you could arrange those pieces. That's more than 10 to the power of 100 different possibilities. And it just turns out you need an incredibly rare event to get there.
The Great Filter offers two possible solutions to the question posed by the Fermi paradox, where is everybody? Everybody never existed, or everybody is dead? If the Great Filter is in our past, it says pretty strongly that we are the first and only intelligent life that exists in the universe. If that's true, then by the Great Filter, there is something, some step, some rite of passage you could call it, that has prevented every other life from reaching the point that we're at. And if that's the case, then we are the only life to have made it through the Great Filter. That means that we can be optimistic about our future. We made it through that rite of passage that has kept every other attempt at life from evolving. It means our big, vast universe isn't wasted on us. It's just waiting there for us to use it. And guilt-free too, since no one else is around to use it. We have a responsibility to put it to use, you could even say. But there's another possibility to the Great Filter too. It may also lie just ahead in our future. Maybe intelligent life is a dime a dozen in the universe, but the reason we don't see other civilizations is because they've all died off. And if all of those intelligent civilizations all died before any of them could make it off of their home planet and spread throughout the universe, the Great Filter is a big red flag for us. It tells us that we should expect to meet the same fate that every other intelligent life has. The Great Filter will spell the end of the world for us, too. To answer the question of whether we face imminent doom or not, we have to look at the evolution of life. And to do that, we have no choice but to turn to the one place where we know life evolved. At the risk of falling victim to the selection bias, we have to look to Earth for clues. We've already talked about how utterly improbable the origin of life appears to have been, but it's probably best to start looking even further back than that. If life emerged on Earth, that means the conditions were right for life on Earth. That's the one data point we have, ipso facto. So the best way to find out what conditions life requires is to look at the conditions of our planet. And it turns out that Earth has some spectacularly peculiar characteristics that make it ripe for life. So peculiar, in fact, that a pair of researchers named Peter Ward and Donald Brownlee rolled all of them up into what they call the rare Earth hypothesis. It's just what it sounds like. When you add up all of its peculiarities, Earth is not like other planets. First, Earth happened to form around the right kind of star. Our sun is a main sequence star, which means it produces light and heat by fusing hydrogen into helium. Main sequence stars aren't rare, they make up about 90% of stars. But our sun also happened to be of the right size, too. It's not so large that it will use up its fuel in just a few billion years. That means that the sun's slow, steady burn would go on long enough to give life time to develop. The sun also isn't too small to support life either. It is, you could say, just right for life. Our sun is also placed in a really great spot in our galaxy. We happen to be located out in the country, in a bit of a backwater when it comes to the Milky Way, about 28,000 light years from the galactic center, in a galaxy that's 100,000 light years across. For decades, SETI presumed that the center of the galaxy would be the most happening spot. That's where the most stars tend to be, and more stars would be more potentially habitable planets. Civilizations that arose in the center might even be in contact with one another, forming something of a galactic urban area. But recently it's become clear that the galactic center might not be so flourishing after all. There are more stars, sure, but more stars also means that there are more collapsing stars, which release bursts of energy that can burn away the atmosphere of any planets in the vicinity. So the galactic center might actually be less of a bustling urban area and more like sterile and dead. Our sun is pretty far away from the galactic center, way out past the suburbs, where nothing much happens, in other words. That's good for life on Earth because it means that it cuts down on the number of sterilization events as life developed over Earth's history, giving it a good chance of succeeding. And Earth just so happens to be located within the sun's Goldilocks zone that I mentioned in the last episode. If it was a little nearer the sun and about 1.5 million kilometers closer, it would be too hot to support life. And much further away, Earth would be too cold for it. It also turns out that where Earth is positioned in the solar system is hugely important to giving life a fighting chance. Earth is the third rock from the sun, with 5 others between us and the rest of the galaxy. 6 if the math that suggests there's a planet 9 out there turns out to be correct. Or if you continue to count hapless Pluto. The sun and the planets in our solar system formed from a massive cloud of cosmic dust. That same stuff that might have blown up so many alien pilots traveling between the stars. We still aren't quite sure exactly how the planets formed. One model, astoundingly, suggested that they could have formed in as little as 1,000 years. But the birth of the solar system was likely a free-for-all grab of the elements that make up the planets today. Initially, astronomers presumed that the planets formed in their current arrangement. But lately it's become clear that that probably wasn't the case. The planets may have actually moved around and migrated from one spot to another in the early life of the solar system before settling into the arrangement that we see them in today. If that's correct, then we were astoundingly lucky that Jupiter ended up where it did. Jupiter's a gas giant, made up largely of hydrogen and helium with a metal and ice core. It's like a sun that never started burning, because it lacked the mass needed for gravity to kickstart fusion. But Jupiter is massive, truly. You could fit around 1,300 Earths within it. It's the most massive planet in our solar system. And because of its mass and its position between Earth and the chaos of the interstellar space outside of our solar system, Jupiter acts as a huge defensive guard for our planet. When asteroids or comets or other flotsam and jetsam bent on destruction enter our solar system, Jupiter's extraordinary gravitational pull draws them into its orbit and slingshots them out back into space. Without Jupiter to run interference for Earth, it would have a steady diet of life-ending bombardments from space. So, thanks, Jupiter. This is astronomer Donald Brownlee. He's one of the guys who came up with the rare Earth hypothesis.
Jupiters are actually pretty rare planets. And so in terms of rare Earth, whether it was Jupiter is good or bad, typical planetary systems probably don't have Jupiters.
Our moon, too, seems to have played a number of factors in fostering life on Earth. Our moon's pretty unusual itself. As far as moons go, it's enormous. It's about 1.2% the mass of the Earth. It doesn't sound like much, but other planets' moons like Phobos and Deimos, which orbit Mars, are closer to asteroids in size. Our moon more resembles a small planet, and because it's so big, it has some very peculiar effects on Earth. For one, it stabilizes our planet. The Earth doesn't sit upright as it spins around on its axis. It's tilted, actually, at about a 23-degree angle. And because of this tilt, we have seasons, which create predictable variations in the temperature of regions on Earth over the course of the year. So when you think about the difference between winter and summer, you get a good idea how much variation a tilt can create. And add more of an angle to the tilt, and the Earth and the temperature variations would become more severe, since during winter a hemisphere would be further away than it is now from the sun, and much closer in the summer. And if you added in some wobble, like if the tilt of the Earth wasn't stable and fluctuated, all of these wild swings in temperature could make it very difficult for life to take hold. The moon's mass actually exerts gravity over Earth and keeps it stable, not wobbling or tilting more than it does, and allowing for a nice, gradual, predictable, and not too varying seasonal temperature shifts. That we even have a moon appears to be a fluke itself. The current view is that the moon was calved off from Earth following a head-on collision in the Earth's early history with a planetoid about the size of Mars called Theia, which the Earth likely absorbed. This giant impact hypothesis explains a lot. The moon is unusually large and unusually close to us because it was created of a mixture of Earth and that fateful planetoid. Because the moon is so close to Earth, it's tidally locked in orbit around us. It doesn't spin on its axis, which is why we always see the same side of the moon as it orbits us. This is an important feature because it also creates the tides here on Earth. As the moon orbits Earth, it pulls the oceans toward it, stretching them out on the ends and narrowing them in the middle. We here on our planet experience this as low tide or high tide, depending on where you are. And it was in these tidal pools of young Earth's oceans where some people think life began. When those ancient tides came in, they deposited a flood of molecules into the tidal pools. And as they withdrew, and the water evaporated in the sun, the increasing concentration of salt could have provided just the right laboratory conditions where those earliest chemicals could combine. Without a moon as large and as close as ours is, these tides could not have existed on Earth, and those early proteins would have lacked that kind of natural petri dish. So the moon itself is a collection of exquisite coincidences that supported life on Earth. But perhaps the most peculiar aspect of Earth is that it has massive plates that make up the crust, which slide along a molten bed underneath. That it, in other words, features plate tectonics.
It's thought that this is a major reason why the Earth has actually had an amazingly stable climate for most, temperatures for most of its age. So it's drastically different than Venus or Mars, which are famously unstable over geologic timescales. So we really owe a lot to this. We don't really know why plate tectonics works on Earth. It doesn't work on Mars. It doesn't work on Venus. It doesn't work on Mercury. It doesn't work on any of the moons. I mean, there are movements of rocks relative to each other, but not plate tectonics of the type that we have here. So we think it's really important.
As far as we know, Earth is the only planet to feature plate tectonics, which acts as a massive thermostat for the planet. When oceanic plates slide underneath the lighter continental plates, massive amounts of the oceanic crust is crushed and absorbed into magma. The rock in those oceanic plates contain huge stores of carbon dioxide. So when volcanoes release magma from beneath the crust, it also contains some of that CO2, which travels as a gas up into the atmosphere. And there it hangs around and it absorbs sunlight, which in turn warms the atmosphere and eventually the planet below. And when the planet warms, more of the oceans evaporate, warming the atmosphere even more. When you have a warm, wet atmosphere, you have lots of rain. That rain brings dissolved CO2 back down to Earth. Rocks on Earth are an excellent store of carbon, and when CO2-rich rain falls on them, it has the knock-on effect of weathering them, meaning the wearing down definition, not the opposite one. All of that carbon in the rocks and rain makes its way to the sea, where it dissolves and eventually sinks to the ocean's bottom. As more carbon is removed from the atmosphere and stored, the planet begins to cool again. Over time, the carbon at the bottom of the ocean forms new oceanic plate crusts, and eventually it will find itself along an ocean ridge, where it collides with the continental plate and the whole process begins again, and the Earth starts to warm once more. This unique property of Earth has kept the planet's climate stable, more or less constantly, for more than 4 billion years, which has allowed life on Earth to grow and flourish. When you take all of these details together, a weird picture of Earth emerges. It's almost freakishly perfect for life. That so many different variables, each at just the right temperature, just the right location, heat, time, whatever, would come together to form a stable whole, seems to make Earth a staggeringly improbable place. You couldn't ask for a better place for life to emerge. And maybe that's the point. Maybe the seeds of life are commonplace in the universe, but Earth is unique. We simply don't know. We still know so little about space, our galaxy, and the universe that we can't say if Earth is freakishly unique or one of many. And as we get better at deducing the existence of habitable planets with our space telescopes, They seem to pop out of the cosmos, like a magic eye poster does when you lose focus in just the right way. Maybe planets that can sustain life are more abundant in the universe than we realize. Perhaps assembling those seeds into life is where the filter lies.
The farther back we look in time, the less we understand. So if you're going to look for something that might be really hard, harder than it seems, farther back in time is the plausible place to look because that's where we don't understand things. And the very first step from completely dead matter to some proto-life, that has to be the earliest step and the one we have the least knowledge of. And more plausibly, it's the hardest step.
Or perhaps not. Perhaps right now the universe is teeming with primitive life. Perhaps the great filter lies somewhere after that. There were, after all, some enormous steps to get from the emergence of life here on Earth and the moment we're sharing between us right now. Back on that early Earth tucked away just so in a solar system tucked away just so in the galaxy, with its volcanoes chugging away at producing a warm atmosphere and its oceans producing a warm liquid medium for molecules to organize into life, at some point, one particular moment in Earth's history, all of those separate components came together to form a full-fledged living cell. As far as we can tell, this moment happened around 3.8 billion years ago. At first, these simple, single-celled organisms were nothing more than gooey bags with the parts for replicating themselves and the parts for converting food into energy, all sloshing together inside of the cell. They spread by dividing into exact replicas of themselves. But over time, over a very, very long time, some new versions of these simple cells began to appear, and they had new specializations. Their interiors became compartmentalized, no longer sloshing together, which meant that the processes they carried out, like converting that food to energy, became vastly more efficient. So processes like photosynthesis were able to develop, and after they did, the oxygen that this early cellular life excreted as waste started to settle into the atmosphere, creating an entirely new one that would eventually support the rise of new types of life. Then comes the invention of sex, a new type of reproduction, where two entirely distinct individuals combine to form a new third version of themselves. And it's about here that natural selection cracks its knuckles and comes aboard as the driving force of evolution here on Earth. When natural selection is presented with new options, rather than rough copies of the same thing, new adaptations emerge much more quickly, which kicks evolution into hyperdrive. The simple-celled organisms that made up life on Earth got better at being living things. And then, for a long time, nothing much changed. It seems as if life had reached a stasis, maxed out, come upon some invisible wall, and taken to coasting rather than progressing toward ever more complexity. Earth seemed content with its vast seas teeming with specialized, extremely well-adapted, single-celled organisms. After that first 300 million years of ceaseless innovation, life on Earth stayed the same for the next 3 billion years. But around 500 million years ago, something huge happened. Life suddenly developed new ambitions, and it exploded into new, extremely complicated and sophisticated forms. And in geological terms, it happened overnight.
Basically, you go from nothing to everything.
This is Dr. Phoebe Cohen. She's a paleontologist at Williams College in Massachusetts.
So the vast majority of the history of life on Earth is that of microscopic organisms. Before the Cambrian, almost all life was microscopic, or at least very, very small. And ecosystems were dominated by things like amoeba and bacteria. And after the Cambrian, ecosystems are dominated by animals. And so it's a really, really huge shift in the biological evolution of our planet.
This sudden surge in complexity is called the Cambrian explosion. We aren't quite sure why it happened. It's possible it was triggered when the widespread glaciation that covered Earth just before it began to melt. Or perhaps it was the oxygen levels in the atmosphere, released by photosynthesis, slowly displacing the Earth's atmosphere of carbon dioxide, ammonia, and methane. We need lots of oxygen to power the conversion of food to energy, and perhaps the Cambrian explosion was triggered when atmospheric oxygen reached a critical threshold that could support more complex life.
So if you go into low oxygen areas of the ocean today, there's plenty of animals living with almost no oxygen, but they're not doing anything. They're very boring. They kind of just lay there because they don't have enough oxygen to do anything exciting. So one idea is that oxygen did reach some sort of threshold around the Cambrian that enabled organisms to start doing fun things like chasing after each other and ripping each other apart. And that played a big role in changing sort of the structure of ecosystems that led to a huge diversification within the animal clade.
Whatever the reason, 500 million years ago, most of the complex body plans that are still around on Earth today suddenly arrived. It's as if those organizing principles of life entered a new phase. Within just 30 million years, plants made their debut on land. And just 40 million years after that, animals followed them out of the water. It's astounding to think of, but within a span of just 70 million years, life on Earth went from nothing but single-celled aquatic organisms to animals that lived and moved and walked around on land. Because life had remained so simple for so long before it, the Cambrian explosion makes an excellent candidate for the Great Filter. It could be so unlikely that it universally denies intelligent life from forming. Evolutionarily speaking, there's never been a more important event in the history of Earth following the emergence of life. 20 of the 36 body plans that exist on Earth today, the plans that give shape to squid and fish and humans and worms, all suddenly appeared on Earth. And those new body plans led to a riot of evolution. The dinosaurs rose and fell, and small mammals emerged from their burrows and climbed the trees. Tree-dwelling apes found their way out of the savanna and started walking upright, becoming the first contours of humans. And it's about here that we arrive at another step in the long span between the emergence of life on Earth and us, the evolution of intelligent life. Humans tend to think of intelligence as what differentiates us from other life on Earth. But instead, we seem more like the current endpoint in an evolution of intelligence. Signs of intelligence in some form or fashion are all around us. In 2008, Japanese researchers showed that slime mold, a unicellular organism, can learn a schedule of electric shocks. When they shocked the mold at regular intervals, and yes, they shocked mold, the mold learned to anticipate the next shock and recoil from it before it was delivered. Mimosa plants have shown that they can learn to differentiate between being dropped and being touched. Where initially the plants responded to both experiences in the same way by curling their leaves, after being dropped several times, they learn to keep their leaves unfurled. And they retain this learned behavior even after they haven't been dropped or touched for months. The use of tools, which we imagine as quintessentially human, isn't unique to us either. Chimpanzees use tools to make gathering food easier, like sticks to draw termites from their mounds by the fistful, and rocks to bash open hard-shelled nuts to get to the meat inside. But at some point, we drew away from the rest of life in the development of our intelligence. We became the first animals to use tools to make other tools. This is the birth of technology. No longer were we relegated to using only what was found in nature. We learned to use nature to fashion new tools to better suit our needs. We made spearheads and axes out of stone and learned to hunt large animals. Meat is more energy dense than plants, and we learned to cook food about 800,000 years ago. When we did, we unlocked a tremendous amount of nutrients and energy that hadn't been available to us before. We developed language, which allowed us to better coordinate ourselves and hunt together and interact with one another more effectively. We learned to make clothes to keep us warm as we spread out beyond the subtropical climate we evolved in. We learned to make boats to carry us to new places. We learned to make ceramics to store our food. We learned to grow crops, which led to cities and the foundation of the modern era. And there was another quirk of that chance collision between the planetoid Theia and Earth which produced the moon. It also produced massive deposits of minerals and metals near the surface that humans could easily get to. Over time, we abandoned those stone tools in favor of more reliable metal ones. And eventually, we put all of those millions of years of accumulated intelligence and technology into ships that broke the bonds of Earth and launched the first of our species into space. Within the astronomically short period of about 100,000 years, humans left the wild and went to space. But perhaps, as unlikely as the emergence of human intelligence may seem, it may simply be the expected outcome of those organizing principles of life. There are two options before us then. Either we humans are unique in our universe and utterly alone, or we are not. And if there is other life elsewhere, then that means that the great filter, the hardest step, lies not in our past, but in our future. It means that the challenge that lies ahead of us is more difficult, more improbable to overcome than dead molecules organizing themselves into living cells, or apes learning to build ships to the moon. And rather than having millions of years to try and fail before succeeding, we will have one shot to get it right. If the great filter lies in our future, then it appears that we are entering it right now. Now, here in the 21st century, 4.3 billion years after life emerged on Earth, we are entering the evolutionary step that no life in the universe has ever managed to survive.
Carl Sagan had this great phrase about humanity has grown powerful before it's grown wise. And our power through technology has been increasing exponentially, but our wisdom has been, maybe it's been increasing a little bit, but certainly not exponentially. And it's getting, these two things have got out of check with each other. We've got an unsustainable level of risk.
The technology that got us to this point is taking a new shape, one that we haven't encountered before, and it is presenting new risks to the survival of our species, and indeed life on Earth. You, right now, are living in what may be the beginning of the most dangerous period in the history of the human race. On the next episode of The End of the World with Josh Clark, if we are the only intelligent life, humans could have a bright, long future ahead of us.
A triple S civilization based on super intelligence, super happiness, and super longevity.
But between us and that bright future lay existential risks, and they're like nothing we've ever encountered before.